So welcome everybody, and today we wanted to present what we've been working on for the last few months as part of InterQ, a machine learning pipeline to perform erroneous data repair. So Erik was the main developer behind the pipeline, so he's the best person to even talk about it. So the talk would be about 20 minutes long, followed by about 10 minutes of questions. So it might be that there are some extra minutes while talking or so, but hopefully we should be on time. So Erik, you could kindly take over the screen and present the pipeline.
Thanks. Okay, so I hope you all can see my screen now. My name is Erik Husom.
Yes.
Yeah, you can see it. Perfect. Thanks. My name is Erik Husom, and I'm a researcher at SINTEF Digital. And yes, Sagar said, welcome to the workshop on erroneous data repair. I'm very happy to get the opportunity to tell you about what we've been working on. I will talk a bit about what erroneous data is and why we want to repair it, and then show you how we have tried to tackle this problem by using a specialized machine learning pipeline. And I will go into some details on how this pipeline works and how it can be used and adapt for many different scenarios and use cases. So let me start by addressing what is erroneous data. In production systems, there can be a lot of sensors monitoring and capturing information about the production process, and the collected data is not always of high quality. It can be corrupt, or it can even be missing entirely. And these problems can have several causes. It can be, for example, electromagnetic noise or thermal errors that make some interference with the sensors. Or if we have some communication failure between the sensor and the data receiver, and that causes us to not being able to record the data correctly or record at all. So the reason why we want to repair this erroneous data is to enable us to have a continuous data analysis by improving the data quality that is needed for a data-driven prediction in manufacturing. And sensor data can be used for different things, for example, quality control of the manufacturing process and the product of the process, and also diagnosing issues and errors in the production cycles. So what we ultimately want to achieve is to contribute to limiting waste and also to zero defect manufacturing, basically. Our approach to this problem has been to look at how we can use machine learning to train models that can replace or repair erroneous sensor values, and do this based on the values from other sensors in the same system. And this is often called a virtual sensor, since the physical sensor is replaced with software, which in this case involves having a machine learning model that attempts to output the actual sensor values based on a certain input. And in order to train machine learning models, we must collect some errorless data from a target sensor, the sensor that we want to be able to replace, and train a model that can find the relationship between the target sensor and the other sensors that we use as an input. An example could be a scenario where you have several accelerometers in a production system, and if one of them breaks down or stops working, you can use the other remaining sensors to estimate the value of the accelerometer that no longer works. To make it a bit more concrete, we can take a look at this figure. I hope you all can see my mouse as well. I will try to guide you through it. So here we have some time series data plotted in gray from several different sensors. And this sensor with subscript I marked in red is the target sensor in this case, which we want to be able to replace, while the remaining sensors are candidates for what we might use as input to the virtual sensor. And when working with time series data like this, it's often not enough to use a single observation in time as input. But maybe we need to use a sequence of observations or an input window, as we see here marked in blue in the figure. And the desired output of a model, the prediction, that could also be either one single time step, or it could be a sequence of values as shown in the red rectangle. So training a model to output a sequence of values can be a bit more challenging to obtain a good accuracy for the model. So often we choose to output only a single value at a time, but then we have the trade-off of being, we have to perform a larger amount of predictions. Furthermore, it's often useful to perform some feature engineering on the raw input sensor data. And we do that to extract some high-level features that might make it easier to train an accurate model. And the model itself, it takes in these input features, and the model is made by a machine learning algorithm. And with time series data, we often use different types of neural networks. Here we have 3 examples. The top one is maybe the most simple type of neural network, fully connected neural network, sometimes called a dense neural network. Then we have the convolutional neural networks, often used in image analysis, and also a long short-term memory network. The 2 bottom types of the network here are particularly useful when dealing with time series data, since they can pick up on the relation between neighboring data points in time, and is often a good choice for the data we have been working with. We use these algorithms to train a model, and the output of this will be the sensor data the repaired data that we want to use to replace potentially erroneous or corrupt sensor. And before I go into the details of our pipeline, I want to clarify the full process of creating a virtual sensor. In this figure, the starting point is at the top left, where we have a batch of sensor data that we want to use for training, which needs to be errorless. So we have a ground truth to work on. And we define the target sensor, in this case in the bottom, and the rest are predictors, which is what we use as inputs. And this is passed to a machine learning pipeline, which does a pre-processing and training the actual model, and at the end, evaluating the model performance. And the last part is done by calculating some error metrics, and also we can do some visual inspection of the predictions versus the ground truth in order to get a feel for the characteristics and behavior of the model in different scenarios. And the resulting machine learning model, if the performance is acceptable, it can be deployed as a virtual sensor that takes production data as input and is then able to output some repair data that can replace erroneous data. So the heart of this approach is the machine learning pipeline, which we have called Erdre, an acronym for erroneous data repair. And it consists of several stages that results in this machine learning model at the end. And this pipeline is quite configurable and flexible. A user can specify many different control parameters in a configuration file that's completely separate from the source code. And the pipeline also stores the output from each stage in cache, and it tracks the changes of the control parameters and the input and output between each stage. So we can easily skip unnecessary runs of stages that we have already run before with the same input and the same control parameters. So we can potentially save a lot of computation time when running a lot of experiments, which often is needed to create and fine-tune models. And I won't go into the details of each stage, but I want to highlight a couple of things that can be particularly useful for anyone who uses the pipeline. And that is, firstly, the initial stage, profiling, where we get an analysis of the training data, information on the statistical properties, distribution, and correlations between variables. So each variable is basically data from individual sensors. In this example, I have some data from a CNC milling machine, We have the X1 output power, Y1 actual position, and also a lot of other variables related to spindle torque, and position, and so on. And all of this is presented in a dashboard for so it's easy to to visually inspect. An important point is this correlation matrix, where we get info on the linear correlations between all the variables, which is very useful when trying to find out which input do we need when creating a virtual sensor for a specific output variable. And there are also some alerts and warnings that might be related to some variables that have constant values or a lot of missing values, for example. So all of this is also stored in a machine-readable format because it's used in the next stage, data cleaning. So all of this goes automatically, but it's often useful to be able to look at it from as a user of the pipeline as well. I want to go into the last stage of the pipeline, which is also quite essential. It's the evaluation of the models. And we test the model on unseen data. We split the data set apart and have some test data that we use to calculate error metrics. And one of the ones we use a lot is R-squared, which is an error metric that we want to have as close to 1 as possible, which 1 would be a perfect match. And it's also possible to have negative R-squared score if the predictions of the model are worse than simply predicting the mean of the data set. But I will come back to this later in the workshop as well, so keep that in mind, that the closer to 1 is better. Also, this figure to the right shows us the training and validation loss during the training process, which is important information when tuning the process for getting a good model. So this is some of the information that you get when using the pipeline. The instructions on how to install the tool and set up everything, it's something I won't go into the details of right now, but the documentation is available on GitHub together with our source code, and I'll show you the link to that at the end. But I'll give you a brief overview. Apart from installing the dependencies and downloading the code, it's a 4-step process. You need to set up something called data version control, which tracks all the assets and the models, and adding data to some specific folders to enable the pipeline to find training data. And then, of course, there are a lot of parameters that can be specified to fine-tune the process. But it's also possible to use a lot of the default values for these parameters when creating models. The last step is actually running experiments to produce the models, which can be done completely from the command line. You can use it locally and send commands to the command line to produce models. But we have also made a graphical user interface for the tool, which can be a bit easier when dealing with, especially when dealing with a lot of different virtual sensors. It has a Python Flask server running at the backend, and this image shows the main dashboard where I have already created some virtual sensors using a dataset from Erdre on accelerometer data. And each of the virtual sensor gets a unique identifier in order to easily distinguish between all the different virtual sensors. In addition, we also show the R-squared score to easily identify the good models versus the bad ones. We have 2 at the bottom, which are quite bad, but also some that have more acceptable performance at the top. So this user interface can be both used to create a virtual sensor and for inference. And when creating a new virtual sensor, you can either fill in this simple form with the name of the dataset and the target variable that you want to be able to predict. But for more advanced usage, you can upload the complete parameter file as well. When you want to do inference, you just enter the ID of the virtual sensor you want to use and upload the input data that you want to run inference on. And This interface at the moment only accepts CSV files, but we have also another option for passing input data that I will show you a bit later. And it's possible to get plots of the results as well when running inference. I'll make an attempt at running a live demonstration now, so hopefully everything works as planned, so you can get a more feel of how things work. I'm going to use a dataset from Erdre on accelerometer data, and this is the profiling analysis from that dataset. We get some general information, take a look at some sample rows from the dataset, where we have a lot of different variables related to the accelerometers. And for simplicity, I'm just going to make a virtual sensor predicting the first one. So what I will start with doing is the first step is to have the data available. I have a small data set here that we will use for training, but it's possible to create virtual sensor for many different things. But I will have to start the server in the background first. You can have it on the side so we see what's happening. And open the tool on this local address. And we want to create a virtual sensor. So what I will do is simply type in the name of the dataset, the name of the folder where the data is located, specify the variable I want to train on. We're going to use a convolutional neural network and a training test split of 70% training data and 30% test data. I submit this and the backend receives the parameters it will use, and it skips most of the stages because I've created similar sensor before, and then it goes on to the training process. And with neural networks, we train for several different epochs. I've limited to quite a small amount to make it run fast, and we can see that we actually get a quite good R-squared score of 0.96, and that appears immediately in the dashboard here. So we can go on to running inference. I'm just going to use the model we just created. And I have made a small test data set we can run inference on in the CSV format. I'm going to plot the results. And hopefully this will not take too long. It should be quite fast. And there we get the result. So we can compare the original ground truth in blue and the prediction in red and see that the model works quite well in this case. So I'm going to go back to the presentation. I think I will be okay. We're back at the start. Just let me move back to the correct slide. Live demo. Okay. So instead of using the graphical user interface, it's also possible to use it through an API that's also included in the server. And the process is shown in this figure where a client can send JSON requests to the API with the model ID or the virtual sensor ID that you want to use and the actual data points, and also specify the names of each variable. And the backend will fetch the correct model and the assets it needs from cache, pre-process the input data, and then run inference through the model. And the result will be sent as a JSON response with the actual output predictions. We can look at one example of how this will look. Very small set of input data with the timestamp of each data point, and we have 2 input variables in this case. And the response will be similarly with timestamps and the predictions for the target sensor. I also want to show you some use cases where we have used this pipeline. The first one is it's from the same dataset from Erdre, but we predict the severity of one accelerometer based on the severity of another. And in this case, we used a long short-term memory network and relatively good performance of 0.71 R-squared score. You can see that the predictions hit quite well, even though it's not perfect. Some spikes that are missed. But it's an example of where you actually can use only one input variable and get output that works quite well. Another case is from a broaching dataset where we predict the x-axis on one accelerometer based on the data from another one. And in this case, the R-squared score is quite bad, and the values doesn't match exactly, but the model is still able to predict the general trend of the output data, even though it doesn't hit the exact mark. Another case is for spindle torque, predicting spindle torque based on the spindle position in 3 axes. Relatively high performance of 0.83, and if we have zoomed in, we would see that in general the predictions matches the ground truth quite well. And finally, another one from a CNC milling machine where we predict the spindle output power from X and Y command position. Also in this case with an LSTM, but if I go back to the previous cases, here we had convolutional neural networks, and in the broaching case, a dense neural networks. So it takes some searching and fine-tuning to find the best algorithm and the best control parameters for finding a good performance in different use cases. So the last thing I'm going to talk about is some of the things that we work on to improve this pipeline. The first thing is uncertainty estimation. And we want to expand the capability of a virtual sensor to also estimate the uncertainty of our predictions. So this figure is the same as the one I showed you earlier, but with an added 4th step where the repair data also gets some confidence interval around the predictions. And the main point is to give information to the user on how trustworthy the predictions are, and also if the uncertainty gets too high, the virtual sensor should be replaced or you should retrain the machine learning model. One method that we use for this is something called Bayesian neural networks. Simply explained, it outputs not single point predictions, but a probability distribution. So you can calculate uncertainties for each prediction. The other thing we're investigating is incorporating explainable AI into the pipeline. We want to be able to understand the models that we create to a greater extent, and which is important for building trust in the models and especially understanding the limitations. Where does it fail and when can it be trusted? There are many methods for this. I think I will not go into much detail since I shouldn't use too much time on this, but there are different methods for neural networks, which in general are black box models, but then we have also other methods like decision trees, random forest, which have an inherent way of finding the feature importance of a model. It has a direct interpretability. So the goal would be to utilize different approaches to be able to give some sort of explanations no matter what algorithm you choose when creating a virtual sensor. And we have one example to the left there in this figure where we have used something called SHAP that can show you the impact of different features on the model outputs. And it's relatively easy or much easier to understand for a human being than the general neural network model. So it offers a lot of useful information. Finally, the source code is on GitHub at this link, and we have also uploaded some documentation on how to use it together with some short demo videos. We also work with work on some research papers where we have used this pipeline. One is already published, this one, where we actually create a virtual sensor for predicting the power output during exercise, during cycling. So this pipeline can be used in many different domains than only manufacturing. We've also submitted a paper on taming data quality, where erroneous data repair plays a large role. And we're also working on a research paper specifically on virtual sensors for erroneous data repair in manufacturing. I think I used a bit more time than I planned, but that was all from me, and thank you all for attending the workshop. If anyone have any questions or want to discuss something, please go ahead, and I'll be more than happy to answer.